When we say topological sort, we are reminded of the sorting algorithms. So we have the quick sort, the merge sort, selection sort, insertion sort, and more. The funny thing about topological sort is that it can yield multiple orders of the items which are all topologically sorted. So if we have a list of integers, distinct integers, and we sort them by a standard sort, be it selection, insertion, quick, merge sort, and more, then we get a single order, a single sorting result of this order list. However, if you have a continuous deployment system where we need to finish some steps before the other ones, for example, we need to finish the compilation before running the tests. However, it's possible that we would want to start running multiple kinds of tests in parallel. And we'll do the deployment to production when all the tests, or to some target server when all tests finish. So we have compile, run multiple tests in parallel, or choose any one of them and run them, and then do the deployment. So when we finished the part of the compilation, we now have, let's say that we have multiple tests, test number 1, test number 2, and test number 3. All of them are now valid for running because we finished with the compilation, we finished with the check style. So this is the funny thing about topological sort. It's that we are sorting something. We are sorting the vertices on a directed acyclic graph, but we can come up with multiple sorts. So it's enough to satisfy the topologically sorted that the next step that we run or the next vertex that we take does not have any incoming edges that were not already satisfied. And we can see this in the algorithm of the topological sort. When the graph is a DAG, a directed acyclic graph, which means we don't have cycles in it, because in the build system, you don't want, in the continuous deployment system, of course, you don't want to have some kind of an infinite loop. Then the way that the algorithm works is first by creating a new array. This is going to be an empty array that would have the in degree. The in degree is the number of edges coming into vertices into each of the vertices. And then we take the first, then we build this in degree array, which means if a vertex has 2 edges coming into it, then its in degree is 2. If an edge has a 0 in degree, then no edges are coming to it, and we can start with it. And then after we have built this in degree array, we scan this array. We take basically all the in degrees, which are 0, and we can run them. And when we run each of these in degrees, we relax the next vertex that this in degree vertex points to. And then when we finish with all of these 0 in degrees, we have another set of vertices which have in degree of 0. So we can continue the process until we don't have any nodes or vertices left. So this was the topological sort, which, unlike standard sorts with distinct integers, we can come up with multiple results of the sort, as long as any item that we come across in the end result of the sort has an n degree 0, which means no edges coming into it. If we have 10 vertices with no edges, this is a DAG. It could be directed, it has no cycles, we just have 2 vertices. We can run each of them in any sort order. And all of these would be topologically sorted. We could take the first node, then the second, then the third, or we could take the third and then the fourth and then the second. And all of these are topological sorts. So this was a brief introduction to topological sort and the difference of it to standard sorting. So thank you all for listening and see you next time.